talk about how characters are represented in memory. We know how integers are represented. We know how floating point numbers are represented. To represent characters, we're still using bytes of data, and there has to be a consistent standard of how a particular character is recorded in memory. So an early version is the American Standard Code for Information Interchange. It's also known as ASCII from the first letters of each word. There are, in this standard, 95 printable, primarily English-related characters, and it's basically the characters on a standard keyboard. Then there are also 32 control characters. The control characters originally had to do with teletype machines, teleprinters. So a lot of those control characters are now obsolete, but they're still part of the standard because once the standard was established, this portion has been left unchanged. And then there's one null character. This gives a total of 128 characters, and 128 different values can be stored in 7 bits. If we start with 0 and go up to the decimal value 127, that can be stored in 7 bits. So ASCII originally is a 7-bit coding standard. Now often the extra bit of a byte is still part of the character, and you just have a leading 0 and that fills out the byte. Later versions of this standard expand things to use that byte in different ways, so that gives 256 characters, and that continues then with more bytes of data to represent characters you can add to the number of characters. But the ASCII standard began to be developed in 1961 based on telegraph codes and how different characters can be represented in different ways. The idea is that we need a consistent way so that everyone interprets the same binary value. When it's supposed to be a character, that it gets interpreted the same way across different machines, different companies, and so on. So the standard doesn't necessarily correspond to any other kind of criteria other than it be clear and precise. This binary value corresponds to this particular character. And so long as everyone agrees that this binary value means this character, then we can communicate on different machines, again, in different places, and so on. So the way the values were determined, the first 32 characters, decimal values 0 to 31, are all the various control characters. And the value 127, we'll see in a minute, is also a control-related character. And the other 95 values are the printable characters. So the printable characters began with a decimal value of 32. Again, this behind the scenes is binary representations of these decimal value numbers. So the 32 corresponds to the printable character space. You can see a space as long as there are things around it. If you just enter a space, then it's hard to tell, is there a space there or not? But the space is represented by the value 32. Then the numbers 33 to 47 are various keyboard characters, and we'll see later how to see which characters correspond to which number. Then the 48 to 57 are the digits 0 through 9 in order. The next few values are some more keyboard characters. And then 65 to 90 are the uppercase letters. Then a few more keyboard characters. And from 97 to 122, we have the lowercase letters. And then 123 to 126, a few remaining keyboard characters, and then 127 is the delete function. So these representations, or this representation of the values becomes accepted, and then we can communicate. If I send this byte from one position, one kind of machine to another kind of machine, then that other machine will also recognize the meaning of that value in the intended way. Sometimes we compare things and say, oh, is this character less than this other character? In other words, we're providing an order to things, and typically we would provide an alphabetical ordering to things. The idea here is that when you compare two of these characters, you just compare to see, is one thing less than the other, based on, is the number representation smaller? And so, for example, in sorting, the digits are sorted before the uppercase letters, and uppercase letters come before lowercase letters. And so the other keyboard characters that are in there, depends on where they're located, which one comes before the other in terms of sorting things. So we're not overly concerned with why these particular values were chosen to mean these particular things. This is the standard. This is the way these values are represented. And so if we are going to do sorting and we want something to happen in a certain way, then we have to be aware of what's going to happen behind the scenes. And if what is going to happen already is okay, then we'll leave it that way. But if we want sorting to happen a different way, we have to adjust or manipulate what's happening so that the behind the scenes doesn't give us results that we aren't expecting. The printable characters that we have available with the ASCII standard are not enough to cover all languages, the different symbols in different languages, or all the different kinds of symbols that we might want to represent. And so over the years, there have been expansions of the ASCII standard. Some things involve entirely new ways of representing. Some build on this standard is in place, now let's add extra bytes that will describe other values beyond just the ones that are in place from the ASCII standard, but don't change the ones from the ASCII standard. So the limitations of ASCII include things like we can't represent emojis in ASCII. But if we had more bytes available, then we could represent these other characters as well. So there are two different mappings that are related to Unicode. One is the Unicode transformation format, which is represented by UTF. And UTF then says how many bits are there involved in the representation. And so UTF-8 is the most common mapping that's currently in use, and it uses 1 to 4 bytes per code point. A code point is a value and its character its character meaning, right? So the value, whether it's a decimal value or the binary value, hexadecimal value, and the value that it corresponds to, or the character that it corresponds to. So you can kind of think of it, if you had a table of these, then a code point is one row in the table. The row in the table saying here's the numerical value and here's the character. So 1 to 4 bytes in UTF-8. It has the maximum ASCII compatibility of all the different UTF mappings, because it ensures that those first 128 values match exactly with the ASCII standard, and then adds extra pieces to that. Then there's another mapping called the Universal Coded Character Set. that is used in different settings as well. So in Python, there are a couple of ways that we can access these values. There are two built-in functions. One is called ord, and the other is character. So ord and chr. So if we want to see the table of ASCII values using Python, we can create those values using one of these two functions. So ord takes as input a single character, and so the docstring for ord says return the Unicode code point for a one-character string. So ord is the expanded version, and you have a one character. Give that to the function, and it will give you back the numerical value. Ord means ordinal, so it gives you back the number that corresponds to that string. Small numbers will be returned in decimal values. Larger numbers will be returned in hexadecimal. Then the character function takes as input a number, and the docstring for that says return a Unicode string of one character with ordinal I. So again, this is an integer value, or again, it can be written in hexadecimal, but you give the number and get back the character, right? You get back what does that thing correspond to. Now the value for I is between 0 and 1,114,111, which is the hexadecimal value 10FFFF. And this idea is that one more than that is the range that we're looking at, 0 to 1 more than this. And so the actual values are from 0 to 1,114,111. So that means that there are a lot more things that can be described in Unicode. A bunch of different printable characters and a bunch of different actions that you want to take. Some things in Unicode require multiple characters to create, so you can imagine some more complicated characters or some characters from other languages that require more descriptive components, emojis requiring more descriptive components as well. So all of these pieces are things that can be presented in Python. We can find these values, we can see what this image is. If you know the number, you can get the character. If you know the character, you can get the number. And we're going to do some things related to cryptography later that will utilize going back and forth between the character and the number. So to see how implementation in Python would work, if we want to output the table of the printable ASCII characters, just those 95 characters in the ASCII standard, we could say, all right, well, for I in range 32 to 127, remember range will start at 32 in this case and go up to, but not including, number 127. So we're going to get the printable characters. We could print I and then print the character associated with I. And so this would give us a table of values. Now it's not laid out nicely, we're not doing any kind of formatting to this, but you can see the number and the character side by side. Or we could, for some other character, just some random character, if we said, hey, what is the character associated with the number 128,528? So these are things you could just try in, say, in the shell if you're using idle. You can test this in PyCharm in a script, and you can see these values associated with each other. You can see how the character function works. Going the other way, we could say, let's create a list of different characters. So ABC, XYZ, and it turns out that the character that we've described here, the 128,528, is this kind of neutral face emoji. If we input that as a string in the list, then we can say, well, let's go through each character in this list of characters. Just called it C, the current character. Then we can print C and the ordinal of C. So you get the character, which we know the characters are the ones that we've listed specifically, and you get the number that's associated with those. And so you can see that there's two different directions we can go. You can start with the number and get the character. You can start with the character and get the number. And as we said, in other things related to cryptography and so on, we need to be able to do calculations sometimes to encode things, and to be able to do the calculations, that's a numerical thing. So we turn the characters into numbers, do the calculations on the numbers, and then take those numbers and turn them back into characters, and that gives you the encrypted value. We'll see all of that in a later video. But overall, the idea is that once you know the encoding, and this is the reason the encoding is very important, the encoding determines the meaning of certain bytes. So one encoding, this particular byte might mean one thing, and in a different encoding it might mean something else, or possibly nothing at all. It might not even be part of the other encoding. So knowing the encoding and being clear and consistent so that different systems can recognize, oh, this is the encoding in use here, let's utilize that appropriately. As usual, feel free to ask questions in the comments by email or on Discord, and have a great day.